morning. My name is Shayan Khalili.
I'm Cynthia Deng.
And my name is Tony Chou, and we study factors related to readership of scientific articles. Imagine you're a talented young researcher trying to establish yourself in a competitive scientific community. The aim of our research paper is to determine how an article can maximize its readership and thus improve its visibility and impact value. This paper analyzed a relationship between a number of Twitter manly views and an article's subject, publisher, journal, and length of title. We also looked at which country has the greatest number of views to see if researchers can garner more visibility by publishing an article relevant to issues in those countries. It is hypothesized countries with higher GDP per capita will have higher readership per million people. And articles about the most read subjects published by established journals and publishers with titles within the ranges of 60 to 80 characters will have the greatest number of readers.
We will begin by giving a general overview of our methodology. Then we will go in depth about our analytical methodology for each factor. The dataset we used was provided by Altmetrics and consisted of 550,000 scientific research papers in the form of JSON files published from January 1st to July 1st of 2016. When it comes to how we gather the data, we use Python's built-in JSON library to extract the number of Twitter and Menly readers and the number of articles for each factor from the JSON files. In other words, we extracted the readership and article count for each subject, publisher, journal, and character length. With that information, we calculated the number of readers per article, allowing us to extrapolate the impact of the factor on a per-article basis. With the help of libraries such as Matplotlib, Pandas, NumPy, and Seaborn, we were able to organize the data into a presentable format. Our primary work environment for writing Python code was Jupyter Notebooks. This IDE is based off of the IPython kernel. With the use of cells in Jupyter Notebooks, it could be much more productive as a result of being able to run cells independently of each other and storing their variables in RAM to be used by another cell later, rather than having to run each script every time a small piece of the code had been changed.
Let's now go into detail about our methodology for each factor. So the segment of code shown here shows how we extracted the number of Menly and Twitter readers for each subject as well as the article count for each subject. To analyze if articles published about the most read subjects have the higher number of readers per article. The code opens each JSON file in the 55 folders individually, checks whether the article has any subject attached to it, and if so, it adds the number of Menly and Twitter readers to the corresponding cell in the subject. In other words, the code tallies up the number of Menly readers, the number of Twitter readers, and the total number of readers for each subject. All of this data is organized into a data structure called a data frame. So data frame is a matrix, a two-dimensional array, that is formatted by the library Pandas to be displayed as a spreadsheet. Similarly structured segments of code are used to extract the variables necessary for analyzing the rest of the factors.
It was interesting how the required data to analyze the relationship between GDP per capita and readership was extracted, as Altmetrics stores country data using alpha-2 codes. This results in a data frame where the index is an alpha-2 code and the data is a number of readers. To convert the index to country names, we exported Wikipedia's chart of countries with its matching alpha-2 codes to a CSV. We then used the spreadsheet to create a dictionary with the country as a key and the alpha-2 codes as a value, allowing us to iterate the original dataset to match the number of readers to a country name. Moreover, since the GDP per capita statistics are absent from the Altmetrics database, we extracted the GDP per capita from the World Bank dataset as a CSV file. We then iterated the original data frame to match the countries with the corresponding GDP per capita.
Once the results for each factor have been gathered, the Pandas method was used to convert the data frame to a CSV file, as to be able to be imported by other programs for graphing. The segment of code pictured here shows how we plotted the subject versus readers graph on the right. Each plot point represents a subject. We began by turning the required columns of the data frame into lists, and then, for this particular graph, we calculated the slope and the y-intercept of the linear regression line, after which we plotted each subject and the regression line. Finally, we formatted the graph by adding a title, axis labels, x and y limits, and the grid. Along with the graph, we printed the R-squared value of the linear regression model to show how closely the two variables were correlated.
For some of our models, we used a bubble chart in order to show additional dimensions of data. For example, in our readership versus journal and readership versus publisher graphs, it allowed us to compare the percentage of articles published in the top 10 most read subjects in relation to its readership and the total amount of articles published. In summary, we extracted the necessary variables, created separate data frames for each factor, after which we performed any necessary calculation before we modeled each factor into a graph to interpret the data. We will now discuss the results of our research.
In our first set of graphs, there's a clear positive correlation between GDP per capita and number of readers per million people, and the GDP per capita ranges of 0 to 70,000 US dollars. This shows us that countries with a higher GDP per capita have a greater portion of the population interested in science. Afterwards, the trend becomes vague as many outliers appear. Many of the outliers represent countries that have a high GDP per capita but are less developed in areas such as personal freedom, according to Forbes. A source of error is that Mandarin readers are mostly Anglophonic, because there's a lack of support at Mandarin for other languages such as Chinese. Similarly, the majority of Twitter users are from English-speaking countries because the platform is banned in countries such as China and falls behind competing social networks in countries such as Russia, resulting in an intrinsic bias in our dataset.
In our next set of graphs, figure 2.1 and 2.2, each plot represents a subject. Figure 2.1 on the left plots the readers per article on the y-axis, while figure 2.2 on the right plots the total number of readers on the y-axis, both against the number of articles on the x-axis. With an r-squared value of 0.84, figure 2.2 on the right shows a strong positive linear relationship between the total number of readers and a particular subject, and the number of research articles published on that subject. However, with an r-squared value of 0.16, figure 2.1 on the left shows a weak positive linear relationship between the number of readers per article and the number of research articles published on the topic. As a result, it indicates that the research article does not have a clear relationship with the readership of an article. The reason we plotted the total readership and the number of articles for each subject is because we were curious as to why subjects with a greater number of articles did not have as great of a number of views per article. As a result, we wanted to investigate if subjects with more articles published actually had more total views. We believe the research topic does not have a clear relationship with the readership of an article, because most research is funded by private corporations, foundations, and governments. Therefore, there will be more articles published on subjects affecting a greater number of people. For example, it can be inferred that subjects such as sports medicine have only a minority of the population interested in them. As a result, it will be more profitable for corporations and beneficial to governments to fund research impacting the general populace.
When comparing figure 2.3, which plots the number of Mendeley readers per article on the y-axis, and figure 2.4, which plots the number of Twitter readers per article on the y-axis, it is noteworthy that Twitter readers are much more interested in medicine than Mendeley readers, while Mendeley readers are much more interested in cell biology and biology. Because Twitter is used by the general populace, Twitter users are more prone to read articles about topics that can personally affect them while scrolling through Twitter. On the other hand, biology and cell biology are popular among Mendeley readers because Mendeley readers are researchers, and meaning they'll be interested in research done in their own field. In general, Twitter users are more interested in topics that will personally affect them, whereas Mendeley readers are more interested in abstract topics.
In both figure 3.1 and 3.2, each plot represents a publisher. Figure 3.1 on the left plots the readers per article, while figure 3.2 on the right plots the total number of readers for each publisher. The weight, which is the size of the bubbles, represents a percentage by that particular percentage of articles by that particular publisher covering the 10 most viewed subjects. There is no clear correlation between the number of articles published and the number of readers per article. However, it can be seen publishers with fewer articles have a higher percentage of their articles about the 10 most viewed subjects. The reason being they are niche journals. Established publishers cannot constantly publish articles covering the top 10 most popular subjects because there are not enough research on those subjects specifically. Looking at figure 3.2, there's a significant difference in the total number of readers between the top 2 publishers compared to the rest. As a result, we can infer a duopoly exists between Elsevier and Nature Publishing Group.
In figure 4.1 and 4.2, each plot represents a journal. Figure 4.1 on the left plots the readers per article on the y-axis, while figure 4.2 on the right plots the total number of readers on the y-axis. Both plot the number of articles on the x-axis. The weight, being the size of the bubbles, represents the percentage of the articles published by that particular journal covering at least one of the 10 most viewed subjects. Similarly to the publisher, there's no relationship between the number of readers per article and the journal in which the article was published in. Moreover, it seems that every journal contains an equal percentage of articles about the top 10 most viewed subjects, as shown by the size of the bubbles. Furthermore, looking at 4.2 on the right, the journal +1 has a significantly higher number of articles than its competitors. However, unlike publishers, there do not seem to be niche journals focusing on particular subjects, nor is the number of readers significantly impacted by the amount of articles a journal publishes.
In figure 5.1, where each plot represents an article, the y-axis represents the number of views per article, and the x-axis represents the number of characters in an article's title. A general trend showing that the shorter title lengths have a greater number of average views per article in both Menly and Twitter can be seen. When comparing the two in figure 5.2, Twitter readership peaks at a shorter title length than Menly because Twitter readers are not specifically looking for scientific articles. Instead, they are most likely scrolling through miscellaneous tweets, thus they are most likely browsing at a higher rate. As a result, they are less likely to click articles that don't have short, to-the-point titles. Moreover, Twitter has a maximum post length of 140 characters. And when adding an article, only around 50 to 60 characters are shown in the preview. Thus, if the title of the article fails to catch a reader's attention in 50 to 60 characters, Twitter users will most likely skip the tweet. On the other hand, Menly users will be looking specifically for scientific articles. Therefore, they will be inclined to read a longer title. The outliers can be explained in the way that the data was generated. It was found by dividing the total number of readers of a certain title length by the number of articles in that certain title length. Consequently, if a particular title length has a small number of articles that has one article with a huge amount of readers, the average is skewed towards that length and therefore have a greater number of readers per article.
The comparison between the number of readers per million people in a country and the GDP per capita in a country indicates that developed countries with a higher GDP per capita generally read more. Therefore, it can be extrapolated that articles can increase their readership by addressing how their respective topics impact high GDP countries. Future studies should track these factors over several years to see if the current trend persists. More importantly, future trend studies should take into account non-English studies, such as Shayan platforms, such as Sina Weibo, Sci-Hub, and AdNat Nikki, in order to remove the intrinsic bias towards the interest and reading habits of English-speaking countries.
On the other hand, the publisher or the journal did not have a significant effect on readership per article. Thus, being published by big publishers or journals is not as important to maximizing the number of readers per article.
However, articles published on sports medicine, biology, cell biology, and computational biology have significantly more readers than any other subject.
The strongest factor affecting readership is the current length of title. A conclusion can be made that articles published with a title length between 51 to 90 characters will receive the greatest number of views from both Menly and Twitter readers.
Although researchers may benefit from publishing articles on topics such as sports medicine or cell biology, it is much more applicable for researchers wanting to maximize readership to address how their topic impacts citizens in developed countries and to focus on writing concise titles between 51 and 90 characters.
We would like to extend our thanks and appreciation to all those who helped make this challenge possible. We would like to recognize Mr. J. Rajasekaran and Dr. Sasha Nukovich for their guidance and encouragement. We especially appreciate Mr. Rajasekaran's background knowledge, patience, and dedication in guiding us through this project. Thank you.
So we're now going to open the floor for questions from the judges for 5 minutes. In the meantime, can I ask that the team that's going third can get up from their seats and start just stand over there in preparation for setting up their presentation, just so things go more smoothly. Great. So questions?
I have one quick question. You have a plot, the bubble plot with yes, this one here, right? Number of readers per GDP per capita. Have you tried to identify, for example, the subject, do the same plot but for different subjects, and then try to pick one that has the best correlation?
Alright, so an extra dimension, like subject to the country?
Yeah, you could be, but I was just wondering if you could do the same plot but for several different subjects, and try to identify the correlations, right? Let's say medicine, maybe for the low GDP per capita, would have a better correlation, right? Right. On the other hand, maybe physics or have a better correlation for higher GDP per capita, right?
Definitely. Unfortunately for this one, we only did country and viewers, and we did subjects separately. But
since the topic we want to analyze is how can researchers maximize their readership, right? So we didn't think it would benefit by looking at which country is more interested in which subject, because since we looked at the subjects and which one's more popular, and we saw that there wasn't a strong correlation. So we were thinking for the GDP per capita, we wanted to specifically investigate if a researcher would benefit, like increase their visibility, if they publish, like for example in the topics, if they provide examples that address these issues in relevant to high GDP countries. Since we found that the subject did not have a big impact, so that's why we didn't investigate that in this study.
I have a question about the Twitter. So the final graph where you're showing the title length. So for the titles that have the optimal title length for Twitter, did you take a look at what kind of topics tend to kind of fit that criteria? So the reason why I'm asking is because perhaps in biology, when you have names of bacteria, the number of characters for that word for that bacteria could be very long in itself. So did you find any biases towards any particular topics for impact?
For title length, no. This is specifically showing how many characters are in the title, independent of subject. But in our subjects to readers graph, we have individual Twitter and Menly to show what Twitter is interested in, what here. If you can go back to that graph.
So it could be that, explaining this graph, it could be that certain topics simply have shorter.
Yeah, that could be a factor. But like Tony said in the previous question, we wanted to specifically investigate what factors affect their readership. We didn't sort of interconnect any of the factors.
Yeah.
Does the fact that somebody looked up a title on Twitter mean that they actually went and read the full article?
No.
Because, I mean, these people have short attention spans. I don't think they're capable of reading a scientific article. It's a way for us to find something that that's trending, but I find this a little disturbing.
That's especially why we also did Menly, in order to compare, in order to get a better understanding of what people were interested in. So by collecting Twitter and Menly, we were able to see what the general populace that browses, these platforms is interested in.
Yes, so unfortunately there wasn't the JSON file did not. Well, we couldn't extract the variable to see if they actually finished the article.
Since the views is just whether or not they clicked on the article,
Yeah.
and even if they exit right away, that still counts as a read.
Okay.
So it doesn't see whether or not they read through the entire article, unfortunately.
Okay. I think that's all the time we have for questions, so a hand again.
Thank you.
Yeah, that's fine.
It's working.
The beginning of course. area one-dimensional.
Oh, all right. Hello and thank you. My name is Kevin.
My name is Chandler.
My name is Haolin.
And my name is Peter.
And we're from Early Secondary School.
Our project was on trends in cancer research and real-world data, a study on optimizing funding for maximum impact. In an ideal world, funding for cancer research will be distributed in accordance with the effect cancer has on society. These stresses can be quantified in various different ways, such as through mortality rates or perhaps new cases every single year. Through the analysis of these variables, we will be able to better understand the cancer research field and develop a solution to optimize funding for maximum impact. So for a report, the reason why we chose to analyze cancer research is because cancer is a leading cause of death in Canada. By taking an overview of cancer research, you can identify the key trends of the field, revealing important information regarding the quantity and the quality of research for different types of cancers. In addition, we can identify possible ways to better allocate the funding that's given to the scientists. Our initial goal was to determine whether there was a correlation between the number of deaths and new cases versus the amount of funding each individual cancer gets. And the number of research papers being published about these cancers is also very important. Our hypothesis was that the more deadly and more common cancer types would receive more attention and finally more funding.
For our research, we used a combination of data analyze tools, including Python, R, and Microsoft Excel. Python was used to phrase through the given datasets, including all research papers that do not contain abstract or Altmetrics words. The output dataset was then analyzed with R. Phrasing to the datasets, R will analyze every occurrences of the given keywords with the abstract of the research papers. For examples, you can see there's an example right there. If the abstract contains the words lung cancer, if the abstract contains keywords of lung cancer, it's actually considered research paper on lung cancers. And then we're using Excel's data on the number of research published for each given field of cancers. Research was compared with real-world data of cancer-related deaths. Additionally, we also considered other factors after we finish our report, such as year of life lost and new case of cancer and such other things as funding.
Using the data we obtained for our analysis for the different types of cancer, we were able to create a scatter plot that plotted the frequency of papers that these cancers appeared in against the number of deaths and the number of new cases in Canada during 2016. The data for the estimated number of deaths and new cases in Canada during 2016 were obtained from the Canadian Cancer Statistics 2016 report produced by the Canadian Cancer Registry and Statistics Canada. Breast cancer had the most number of papers published about it with 1,695 papers, 4 times more papers than the second most published cancer, prostate cancer. Despite lung cancer causing 20,800 deaths, 2 times more deaths than the second deadliest cancer, colorectal cancer, it ranked third in the amount of research papers with less than 4 times the number of papers as breast cancer. From this, we gathered that if the importance of dangers of cancer were based solely on deaths that the cancers cause, breast cancer research is favored far more than other types of cancers, while lung cancer does not receive the attention that is warranted. For the frequency of the research papers versus deaths, the data followed a positive correlation with most of the data points clustered in a section with a low amount of deaths and low frequency. 2 clear outliers were lung cancer and breast cancer, with breast cancer having a large amount of research papers published about it despite not a lot of deaths, and lung cancer having lots of deaths despite and not having a lot of research papers. For the frequency of research papers versus new cases in Canada, the data mainly exists in 2 clusters, with breast cancer being again a clear outlier. Breast cancer has a much larger amount of research paper than the other cancers. Prostate cancer, lung cancer, and colorectal cancer all had large numbers of new cases and did not have a large number of research papers.
In addition to new diagnosis and mortality rates, we also investigate some new factors post-report that could potentially affect research output of each individual cancer field. The first factor we investigate was year of life lost. Year of life lost was a measure of how many years of life was lost due to a cancer disease due to a premature death. For example, if you are expected to live for 6 years, but you only live for 10 years due to the cancers, that's expected to have a year of life loss for 50 years. This metric places emphasis on cancers that affect people earlier in their life. Thus, you will see, you would expect a drastic shift in the graph, especially from cancers that affect the youth. Yet, graphing out this metric is receiving the same general overtrends, with breast cancer and lung cancer being the outliers in terms of research produced. This indicates that breast cancer is constantly overfunded, even adjusting for many different metrics, as well as the fact that lung cancer is constantly underfunded.
So, the last metrics we looked at is funding. So, we looked at what might affect research output for funding, which funding is what correlates the strongest with the amounts of research produced out of all the other metrics. So, this suggests that investment into cancer research results in. This suggests that investments into cancer research results in proportional returns, meaning that the higher investment, the greater the return. This further supports the need to reinvest in lung cancers, as there's a good correlation for at least a proportional return. So this is our overall data graph for every single metrics that we considered. So as you can see that over there, breast cancer has clearly a lot of funding, but not a lot of funding, but relatively low amounts of death. And lung cancer has high amounts of death, but comparatively low amounts of funding. So this is another graph taken from the Canadian Investment Report 2013. This is not our graph. This shows the same clear trend with lung cancer being underfunded but having a lot of deaths, and breast cancer overfunded with relatively little deaths.
As well as looking at the frequency of the research papers of each cancer, we decided to look at the Altmetrics scores to determine the attention that research papers on individual cancers receive. Of all cancers, colorectal cancer had the research paper with the highest Altmetrics score at 1,623, with breast cancer following behind at 1,031. Notable cancers that had a high max Altmetrics score despite having low amounts of research papers were brain cancer, that had a max Altmetrics score of 748.2 in 19 research papers, pancreatic cancer that had a max Altmetrics score of 820.5 in 164 research papers, and ovarian cancer that had a max Altmetrics score of 740.8 in 186 research papers. The high Altmetrics scores could be because of the low number of reports that pertain to these cancers, resulting in the ones that are received gaining more attention. Alternately, the scores also suggest that research of these cancers gain attention and support. However, the attention is being undervalued and not enough research papers are being published. We also looked at the mean Altmetrics scores of research papers for each cancer. We noticed that brain cancer had a very high score, suggesting that brain cancer research receives support and attention and should have more research papers published about it. Once again, breast cancer seems to have too many research papers for its average mean Altmetrics score.
A possible reason that breast cancer receives more research than any other cancers could be because of the large media and societal attention that it receives every October during Breast Cancer Awareness Month. During this month, organizations of facets band together to raise money and support of breast cancer research. Every season for the past 8 years, the National Football League has been supporting the National Breast Cancer Awareness Month by starring its players in pink attire and using pink decals for the game ball and the field. This not only generates proceeds for the breast cancer research, with 100% of the proceeds of all pink merchandise sales going towards funding, but it also influences the millions of fans all around the world.
So, through our analysis of Altmetrics data, we have concluded that mortality rates, new diagnosis per year, and years of life loss do not have a strong correlation with the amount of research produced, and therefore does not fit societal needs. Funding correlates strongly with research as expected, and the altercation of funding is necessary to implement a more ideal system of cancer research. Further analysis of our data revealed 2 individual cancers, lung and breast cancers, which are consistently the outliers in spite of multiple different metrics used for analysis. This reveals a clear problem with the allocation of funds for cancer research, with the underfunding of lung cancer and the overfunding of breast cancer. In addition to frequency data, we utilized Altmetrics stores to reveal the quality of research overall in a given field. We found that some cancer research, such as brain cancer, despite containing relatively small amounts of research papers, have high-quality papers with high Altmetrics scores. This could imply that papers are valued because of their scarcity, or these fields of study are undervalued. We recommend the redistribution of funds on key fields of cancer research, particularly in breast cancer and lung cancer, to better optimize the scientific community to provide the most benefit to society. Our findings are also supported by multiple studies which reach similar conclusions. For example, a study published last year, April, in the peer-reviewed journal Oncology Reports reached the similar conclusion to our finding. Their research used data from the Canadian and American Cancer Society to determine that overall research output is not well correlated with public health burdens of individual cancers. Another report, published by the American journal BMC Health, also reached the same conclusion, indicating a similar trend across the board. They also concluded similarly that scientific progress in cancer research is not reflective on the needs of society, and that a redistribution of funds is needed in order to increase the effectiveness of research.
Thank you. Thank you. All right, so once again, now for questions from our experts. If the fourth team could get ready to start as soon as the question period is over, that'd be great.
So I have a question about, for example, you identified lung cancer, right?
Yes.
So probably there is not many more research done because they already know, for example, smoking increase the risk of getting cancer in fields, right? Did you identify on your data, how many of those cases are related to smokers and how many of those are not?
No, we did not correlate the smoking with lung cancer because we knew that everybody knows that cigarettes lead to and tobacco lead to lung cancer, and that because of this, the medical research is lowered because we already know how to solve the problem. But breast cancer is still extremely overvalued and has lots of media attention despite not being as deadly or as more diagnosis as other cancers.
Okay. My second question is, what about the methodology that these studies use? Maybe for a particular field, it's more expensive to do research than another field, right? So, was it possible to extract that from your data? Or?
Yeah, I think it's very difficult to quantify like the effect, like hardness or methodology like of a field. So we didn't really consider that, but we have thought about it, but we weren't really able to quantify that in a number, so to chart it out or something. Yeah.
Okay, thanks.
Could you go back to the slide that shows the number of cancer occurrences in Canada?
Deaths or new cases?
This is the one you're talking about?
Yeah, I think that's okay.
This data was obtained from the Canadian statistics report.
So the number of deaths in Canada for breast cancer is 5,000. The number of new cases is 26. And lung cancer, so more people are dying from lung cancer, and yet the number of new cases is for the most part equal for breast and lung. Is that correct?
Yes.
So to point out, I think we need to be a little bit careful in our interpretation of new cases here. It could be that the diagnostic measures for certain types of cancer have improved, and that may have resulted in a higher number of new cases. It could also be because of the population growth as well, so it's not normalized for people who were dying in 2016 are different from people who are still alive in 2016, so there's a timeline, that's right.
It could be because of the result of the research as well, right?
Yeah, absolutely.
Sorry, just so the data for the prevalence and the death are for Canada, right?
Yes.
Funding is also for Canada?
Yeah.
Yes. Okay. And also the research articles, were they just for Canada?
One was from American, so
Just one? No, I mean like generally the scores if you calculate from Altmetrics.
they're all from Canada.
All from Canada. And because prevalence for breast cancer is by far the highest for women. And so, I mean, those are some of the factors that you may want to look at, especially like in combining death and prevalence, like making it a normalized score of death and prevalence together and then seeing how if you would have outliers there. Because it will, the reason that lung cancer has received like less attention is a combination of the high death rate but lower prevalence. So those are some things that you may be interested in.
Is there any more questions?
Well, that's also about all the time we have. So thank you again. So I'd like to let everybody know that after this fourth presentation, we have a short break. There's a table full of swag generously provided from Digital Science and its portfolio companies, Altmetric, Overleaf. So please help yourself to those. And yeah. Great. So I'll let you guys know when you hit 12 minutes, all right? And you have 15 total.
Good morning, everyone. I'm Emily, and my teammates Leon and Curtis, and I have used statistical analysis to develop a model that takes in various atmospheric factors to predict forest fires. And through this, we were also able to analyze the impact of climate change on worsening forest fires, and will make some suggestions as to some solutions that will minimize the harm. So just for a brief overview, every year Canada experiences about 8,000 forest fires, each burning between 0.7 to 7.6 hectares. And this is an increase by 50% of the 10-year average, and the frequency has been higher than the 10-year average. Now, these fires have evidently resulted in many serious damages. For instance, we are all aware of the recent Fort McMurray coast fire, which resulted in 125 evacuations. This released many toxins and pollutants into both the atmosphere, in lungs, and the water system. And it also racked up damages between 4 to 9 billion and caused 14 days of lost oil production. Now, annual fire suppression costs are also between 500 million and $1 billion. So, as we will discuss further in the study, climate change is a huge factor to forest fires and their behavior. As of now, Canada ranks 15 out of 17 OECD countries on our CO2 emissions per capita rate. And we are actually about 3 times greater than that of Switzerland, showing that we have a lot of room for improvement. And in fact, 81% of those emissions come from our energy sector, which includes combustion sources, transportation, and fugitive sources. Now, our Prime Minister Trudeau has planned to cut emissions to 523 megatons of CO2 equivalent by 2030. However, that, as you can see in the graph, that number is much lower than our numbers from many previous years. And also, recent policy decisions, such as the Kinder Morgan pipeline and the Line 3, has added a lot of CO2 emissions into the atmosphere, making more people skeptical of our ability to reach that goal.
Okay, so to begin our analysis, we first took data from the National Fire Database, which archives our forest fire data from 1949 to the present time, but our analysis only goes up to 2015. In addition, we concatenated this data with the historic weather archives to gather features that we may want to use during our analysis. These will be climate features such as precipitation, temperature, and wind speeds. And furthermore, we also moved on with some of the Sustainable Forest Management Canada stats to determine what is the burn rate for some of the forests that may be happening in Canada. And with these features, we use our analysis.
So as you can see from this graph, from the National Forest Fire Database, we were able to extrapolate the number of forest fires that occurred from the past 70 years. So since 1945, you can see that the number of occurring forest fires has been increasing at a steady rate. Hence, forest fires are becoming more of an issue. From these forest fires, we were able to determine three variables that were associated with how the forest fires were created. One of them being temperature. So the main group of forest fires that happen, the temperature is around from 5 to 20 degrees Celsius. That's where most of the fires happen. However, in drier conditions where the temperature falls below 10 degrees, negative 10 degrees, despite there being lower temperatures, the humidity in the air has also been less, therefore enabling drier conditions for the fires to occur. Precipitation, it kind of shows an inverse relation. As the precipitation goes down, the size of each affected forest fire also increases. The wind speeds that were determined from each of the fires, the greater the wind speeds, that lets the fires be able to develop more faster. However, over a certain limit, it starts to cease.
Sorry to interrupt your presentation.
Yes.
Just press the button on the mic to actually activate it.
Oh, sorry about that. We were able to organize the forest fires into 19 distinct regions. Each of these regions we assigned a value or just a region identification number. From this, we were able to determine the types of trees that were affected, as well as the burn rates, which we assigned either slow, medium, or fast, depending on the types of trees that were affected. For example, coniferous, deciduous trees, and also there were some grasslands, areas of tundra, etc. These points, the colors have no meaning themselves, just to distinguish each point from each other. However, based on this, you can tell the section where you have a large cluster of points resembles the shape of British Columbia. Since British Columbia has a lot of forest there, as well as it's largely affected by forest fires.
Okay, so for analysis, we want to first predict what were some of the size of forest fires that we can actually predict to see how large the size of forest fires were based on variables that we discussed earlier, right? So first we began with the 5 variables we mentioned: precipitation, temperature, wind speed, and including month and the burn rate of the forest fires. So to reduce the dimensionality of this data frame or this matrix, we use principal component analysis. So we actually merge these 5 data points into a single axis, and then we applied it against the size of hectares of it. So through this, we then ran a simple linear regression algorithm to try to find, to try and predict where some of the values. We want to do some polynomial regression or logistical regression to basically meet some of the outliers, but ran into time constraints and we weren't able to do that, unfortunately. So with this linear regression and analysis, we first looked at some of the climate projections that that we have researched. And so this is some of the climate projections that would happen if Canada or the rest of the nations of the world did not partake in something known as the Paris agreements. So if these were some of the variables that we inputted into our regression, and so with that, these are some of the variables that would happen if we were able to meet the Paris goals in the future. And you may notice that the temperature is a bit lower, is because Canada's further up north and we're trying to get below the 2 degrees Celsius. But anyways, here are the results from the regression. So with the Paris commitments, the average hectares would be, it should be 1.1 hectares. But anyways, without the Paris commitments, you could obviously see that there is an increase in forest fire burn. So multiplying this by the difference, we would get 278 hectoliters saved for every single forest fire. For every single annual year on average. So one way that we wanted to do was to reduce the number of forest fires. So we thought to ourselves, how can we reduce the number of forest fires, or how can we minimize some of these variables that are causing these forest fires? So we thought of how about wind farms. So wind farms are really great for forests because when we have wind farms, we have giant lightning rods basically to attract lightning and to basically reduce the amount of forest fires. 40% of our data set of the that caused these forest fires were actually caused by lightning-related causes. So we could reduce the amount of lightning, we can reduce the amount of sparks, and reduce the amount of force in total. Furthermore, it will also offset our greenhouse gases as we can move on and transition into cleaner fuels, and we can also put off our coal energy power plants in total. So we first applied all the forest fires ever onto a map of Canada. We wanted to do a nationwide regression or analysis. So you see those blue dots. Those blue dots are clusters, or where centroids of where we should put these wind farms in. So we use some simple K-means algorithm to basically identify these clusters. We used 200 clusters during this analysis because we wanted to, because based on previous years, last year Canada put up 41 new wind farms, and within the next 5 to 10 years, we believe that it is plausible to put up another additional 200 in these forest areas. Okay, so, but since that was national-wide prediction analysis was a bit too sparse, we wanted to get a high-resolution data. So we looked into some of the most dense locations in Canada, which was Northern Alberta. And Northern Alberta, if you look at the slide prior, had a lot of forest fires, and we wanted to say, where should we place these wind farms to basically minimize the effects. So the reason why we did the clustering was so that we can maximize the area of effect per wind farm over an area and to reach the amount of forest fire locations. So this is the location. Okay. So K-means is a divisive algorithm, right? It goes top down. We have all these clusters to basically determine where the centroids are. We also tried to do some algorithmic analysis, which is a bottom-up spectrum, but we found that it wasn't really that helpful during the analysis. You guys can look at the Shayan points. The Shayan points was another algorithm called mean shift. We tried to mix in different algorithms to try to locate these wind farms, but as you can see, they're really close together, and it wasn't really determinative of possible wind farm positions. So that was some improvement that we can work on.
Right, so our team is aware that data analysis and statistics is a very powerful tool. However, what is more important are the implications and conclusions of our actual study. So here are some policy recommendations and overall recommendations that we will make. So in addition to the wind farms, we recommend prevention of forest fires, which can reduce the suppression and rehabilitation costs to 30%. So some prevention policies include regularly thinning out young trees to reduce forest densities that are above average and burning ground litter to restore natural conditions. Another method which does need more testing and research is cloud seeding, which is essentially weather modification, which whereby shooting various chemicals into the atmosphere, we can increase humidity and increase precipitation. Now, this may not suppress forest fires in the long term. However, it may reduce its effects or perhaps delay it to allow more time for the government to make adequate evacuation policies or any other decisions. With respect to the future direction of science as a whole, we first recommend developing more accurate models to accurately forecast the intensity and precise location of imminent forest fires in order to allow a more accurate prediction of the harm that they may cause. We also would like to track the greenhouse gas emissions of other sectors beyond energy, such that we can tackle climate change as a whole and, as a result, reduce the harm of forest fires. Some very important actions that the government needs to take and what we are trying to encourage is to reduce our overall dependence on oil and fossil fuels. As you are all aware, our economy is largely dependent on oil. However, that is causing a lot of detriments to our environment. So we first advocate for removing fossil fuel subsidies, which are currently at $3.3 billion. And with that measurement, it equates to about $19 for every ton of carbon dioxide equivalent emitted. Now, another thing that we would really like to support is increased funding, subsidies, and grants for the research, development, and innovation of green energy and green energy companies. Green energy is definitely a product that will highly be in demand in the future, and Canada needs to be a leading country in encouraging this innovation. So also by having the wind farms set up, we can reduce our dependence on oil and have a source of revenue that hopefully can be directed to the research and development of these firms. We truly believe that in order to tackle a problem as interdisciplinary and multifaceted as climate change, we need to combine the informational and social sciences of academia and industry, public policy, and private firms. And through this, we can hopefully make a dent in stopping climate change and reducing the harm of forest fires. Thank you.
Questions from our experts?
I have a question about these wind farms. So I assume that, and correct me if I'm wrong, but wind farms need a certain level of wind. Did you incorporate that into your analyses?
Yes. So based on the wind speeds that we determined for different regions of Canada, especially near where forest fires have occurred, we decided to place wind farms in those locations optimally, such that the wind farms they prevent lightning from, they reduce the chance of lightning actually hitting the trees, so they act as lightning rods as well. They convert the kinetic energy from the wind into electricity, which can then be used to power various things.
To add on, there's also the Arctic airstream that runs throughout the boreal forest regions, and that is a major source of wind for these wind farms. And so yeah, there's a lot of them.
So I have a question. Do you know of any pilot project for these wind farms and the effect on the neighborhood of this wind farm?
So you may have been aware of electricity prices in Ontario and how there are many people that have been complaining on it, right? These wind farms are actually great and they will not impact people that much, is because they'll mostly be in desolate areas, and in desolate areas you won't have as many negative health effects on people as well. And furthermore, we will be building roads to get to these wind farms, and in addition, that will also help emergency fire crew, right? So effectively, it will not damage the environment, well, the neighborhoods, or affect anyone else nearby, and as it will be away from society.
Recently, in the past 5 years, there has been an upward trend of about an 18% increase in the energy generated by forest farms per year. In 2015, there was a $1.5 billion investment. Now, the issue is that many of those farms are built in Ontario and Quebec, where of course they are producing electricity, but we believe they can also have other benefits if they were produced in more strategic locations like in Alberta, BC, and in those centuries. Yes.
Isn't it a little illogical to put wind farms inside a forest? Because, these things need to be, or at least in my naive way of thinking, they have to be in an open area, usually higher up, or where there's no impediment to the flow of wind. If you do it in a forest, you're kind of blocking the wind anyway.
The turbines are usually way higher than the trees itself. They're like several hundred feet in the air, so the trees will not block the wind.
I guess installing them would be difficult.
Yeah, it would be difficult. You have to chop the the forest and build roads and all kinds of stuff.
So adding on to what Curtis mentioned, a lot of the times the turbines wouldn't be just in the middle of the forest. They can also be placed as a boundary around regions of many trees, so that way incoming air is just powers the turbines. So it wouldn't be just in the middle of nowhere.
How far is the range of a lightning rod? No, I mean, seriously, is it 50 kilometers, 100 kilometers? When you have lightning, I don't know that you can actually direct it to a lightning rod that's 100 kilometers away. So.
Yeah, exactly. That's why we want to do the higher resolution analysis. They're usually around less than a kilometer. As you guys seen the CN Tower, right? It keeps getting hit by lightning several hundred times a year. And collectively, with all these wind farms, they will be higher than the tree tops, and so they will actually have a higher chance of hitting the turbines and the actual trees itself.
So it may be more cost effective to have lots of lightning rods than.
Sure. I think our original intent with the wind farms was to generate electricity and reduce the wind speed, because wind speed blows oxygen into the fire, it helps spread the fire, and lightning rods was kind of an additional benefit. And I think what you mentioned were definitely very good points, and I think factoring in the actual land available for wind farms and having more accurate prediction are definitely some next steps that we should take.
I think that's all the time we have for questions. Thank you again. Right, so I believe we have a break now. If I could find Mark.
Everyone, just quick attention. If you have any dishes or food in here, just ask.